Hi, my name is Shaheen Rabbani, also known as Amir Hossein Rabbani. I'm presenting our latest work on real-time fluid simulation using a novel technique called Poisson filters. This work is done at Laforge R&D Ubisoft Montreal in collaboration with McGill University. We introduce a non-iterative, non-data-driven, and GPU-friendly pressure projection solver called compact Poisson filters to simulate Eulerian fluids in real time. Our method achieves up to 10 times faster simulation runtime and up to 30 times faster projections, making it possible to simulate the notoriously expensive Eulerian fluids at interactive rates in high-resolution domains. In this video, we are going to examine the problem, which is solving the famous Poisson equation in the context of Eulerian fluid simulation. We go over the details of our modal GPU-friendly solution, then we see the performance results as well as some demos, and finally we see how Poisson filters should be implemented on GPU to maximize the performance. So what's the problem we're solving? We solve for the Poisson projection step in Eulerian fluid simulation, which is often quite expensive, but equally important in mass conservation in incompressible fluids. This step is directly related to solving the famous Poisson equation. So the problem to solve is, given a divergence of the velocity field omega, what is the pressure that satisfies the Poisson equation? This pressure is used to correct the velocity field to achieve mass conservation. Solving this equation is one of the most crucial steps in achieving real-time fluid simulation. To understand the importance of this step in real-time applications, we can look at how much it costs. In Eulerian fluid pipelines with traditional CPU-GPU iterative solvers, a big chunk of the computation is spent on a single projection step. For example, in 2D and for a typical relative low number of solver iteration value of 32, almost 83% of the total computation is spent on projection. This is the bottleneck that we would like to improve. We need sufficiently large numbers of iterations because the more iteration we have, the higher visual quality we get from the simulation. The same cost-quality ratio, more or less, is true for 3D solvers as well. This bottleneck becomes more important knowing without the projection step we basically have no fluid, and the velocity field doesn't evolve much. There are a lot of solvers out there to do this. GPU iterative solvers are the most common methods in interactive applications because they don't need any pre-computation for object collision, but they are often very expensive. GPU-based spectral methods often require a pre-computation step for object collision, which makes them not suitable for interactive applications, but they are fast because they are parallelizable. Machine learning methods are somewhat flexible for object collision, and they are fast, but they are often hard to reproduce and hard to generalize to cases outside the training dataset. Poisson filters sit nicely on a sweet spot in between iterative and spectral methods, combining their benefits and avoiding their drawbacks. To solve for the Poisson pressure, that is also known as the inverse Poisson equation, we can pre-compute Poisson filters and convolve them with the fluid domain to get the pressure, where each filter takes care of a different spatial frequency in parallel when convolved over the field. This means the final pressure is a modal solution to the Poisson equation. Our filters can be used to solve the heat diffusion problem as well, which is categorized as the forward version of the Poisson equation. Here you see examples of order 50 rank filters for the 2D case to solve for the inverse as well as the forward Poisson equations. These are non-iterative, one-shot convolutional filters that are very much GPU friendly, meaning all filters can be applied to the fluid in parallel, each contributing to the modal solution for certain spatial frequency. Later in this video, we will see how these filters are computed, how they are applied, and more importantly, why they work the way they do. In general, spectral methods approximate the solution, while finite difference methods approximate the equation. Poisson filters sit nicely on a sweet spot in between, where we approximate the solution based on an approximation of the equation. This way, we get the best of the two worlds, meaning all the good stuff from spectral methods like parallelism and all the good stuff from the finite differencing method, like easier treatment of boundary condition when the fluid colliding with the objects. In a nutshell, Poisson filters are local operators mimicking a global solution. Compared to a typical fast GPU-based iterative solver like Jacobi, Poisson filters achieve an order of magnitude faster projection and simulation for a large number of iterations, like 200 iterations in this example, without loss of visual quality. Our method also enforces Neumann boundary condition for both static and dynamic colliders. Poisson filtering is significantly faster than traditional linear solvers like Jacobi, Gas Idle, and PCG. It runs entirely on GPU, is simple to code, it can be used as a drop-in replacement for current iterative solvers and grids. It works both in 2D and 3D. It also works for both cases of the Poisson equation, meaning inverse and forward Poisson. We will show examples of each one in the form of pressure projection as well as heat and density diffusion. Our method supports Neumann boundary treatment when colliding with objects, and we also show how Poisson filters provide a local view to the spectral methods. Okay, let's see how we do it. In the Navier-Stokes equation, we have the zero divergence condition on the velocity field that ensures the fluid remains incompressible. One way to solve this is through the Helmholtz-Hodge decomposition theorem that tells us that the divergence of the velocity can be corrected by subtracting the gradient of the resulting pressure field. To solve this, first we need to solve for the pressure using the Poisson equation, where omega is the divergent velocity. To solve the Poisson pressure equation using the Jacobi solver, we form a linear system Ax equals b, then we decompose A into lower and upper triangles and a diagonal matrix, and iteratively get better estimates for the unknown x through this update step. The benefit of this approach is that we don't have to explicitly compute the inverse of the Laplacian. Also, Jacobi is highly parallelizable and hence GPU friendly. In coding, it actually translates to something very simple. For example, in 2D, given the divergence d for n iterations and for each cell, we update the pressure value of the central cell using its 4 neighbors. In 3D, we would have 2 more neighbors, of course, but let's stick to 2D for simplicity for now. While the inner loop is a small kernel on GPU and very fast, the CPU cycle makes it very slow. So let's see how we can get rid of the CPU side. If you look closely at the updated step, you would notice a recursive structure where xk plus 1 always depends on its previous value while everything else remains constant. So we can analytically compute a convolutional kernel that exactly matches the target Jacobi iteration of k that gives us the corresponding solution xk, which is a solution after k Jacobi iterations. B here is the right-hand side in the linear system Ax equals b. So this way, we effectively replace the iterative solver with one-shot convolution. Let's see how we grew the convolutional kernel. Read this as f of order k. I'll later explain what this order actually means. Okay, let's take a look at the GPU update line that we saw earlier, and let's investigate how the recursive behavior emerges naturally from this line in the Jacobi updated step. Given the input divergence as DC, to get the value of the pressure for the current cell, PC, we need to get its 4 neighbor pressure values at the current round of the Jacobi iteration. This means we need to know, for example, the value of P West at the last round, but in there we see P West was also computed from its 4 neighbors at the previous round, and same thing for P East and P North and P South. You probably already guessed that we can repeat the same unwrapping for the cells in the previous round to go even further back in iterations. And you're right, that's exactly what we do. This unwrapping process gives us a recursive structure. As we unwrap more cell values back from the previous rounds, we reach more and more cells, collecting more and more information about the pressure in farther parts of the domain. And the kernel emerges gradually. If we do this k times, we get the kernel f of order k that precisely matches the result of a Jacobi solver after k iterations. Remember that this is a backward process, which means if, for example, we are interested in a kernel that mimics 10 Jacobi iterations, we are starting from the 10th iteration and going all the way back to the first iteration. So reaching the first iteration is always the base condition for our recursion. So far, we only talked about solving the pressure projection problem. We can show that a similar update step can be used to solve the heat diffusion problem because of using the same implicit Poisson operator inversion. More generally, when solving for a new value of x at the next iteration k plus 1, given the right-hand side b, we can introduce two scalars, alpha and beta, in our updated step, and then set the value of alpha and beta depending on whether we are solving an inverse or forward version of the Poisson equation. This gives us a nice unified kernel that can be used for either types of the Poisson equation. Remember, when we say inverse and forward Poisson equations, we mean in the inverse setup, f is given and phi is unknown, and in the forward setup, phi is given and f is unknown. People call these equations different names, but we find it more helpful to introduce our own terminology. The right-hand side B can be the central thermal in case of solving the diffusion problem, or divergence if you're solving the pressure projection problem. Now, to grow our kernel, we need to plug in the right alpha and beta values. Alpha is computed from the cell size only for pressure projection, shown here as delta x, while for diffusion, we also need to include diffusivity coefficient kappa and the time step delta t. Beta simply controls if we are doing things in 2D or 3D, and in the case of solving for diffusion, it needs to know about alpha as well. Please note that we have now two more neighbor cells in 3D, back and front, which are shown by subscripts B and F here. You can find the details of deriving alpha and beta in the paper. Now, here is an important detail to pay attention to. In the kernel growth equation, we intentionally use uppercase X and uppercase B to indicate that our system is not in the vector form, or as we would like to put it, it's in the matrix form. This means it doesn't matter if we work with a 2D or 3D fluid domain, we keep its dimension as is. So in 2D, the system Ax equals B consists of 2D matrices, and in 3D, everything is a 3D tensor. This is contrary to more familiar vector form linear system Ax equals B with lowercase x and lowercase b that you typically see in textbooks, where the domain X as well as the right-hand side B are flattened to become vectors. The benefit of keeping things in the matrix form is that it makes a couple of things a bit easier. One is that treating the boundary condition becomes easier to formulate, and the other one is our GPU implementation becomes more straightforward, as you will see later. Again, please see our paper for details on the difference between these two forms. We can visualize how a Poisson kernel grows as a function of alpha and beta that are collected recursively and over multiple iterations. So for example, in 2D computing, an order 1 kernel corresponds to the result of 1 Jacobi iteration. As we do more recursions to get higher order kernels matching higher target Jacobi iterations, an interesting staircase structure shows up. In practice, we don't need to compute anything symbolically like this, and we just recursively collect alpha and beta coefficients in our code. Here you see an animated visualization of an inverse Poisson kernel growth for a 2D domain and for a cell size delta x equals 1 and the dimension d to be 2. From these values, we get our alpha and beta values and plug them into the unified kernel equation. As we increase the target Jacobi iterations, our kernel gets more and more refined in terms of extension and smoothness. Basically, as the kernel order grows to higher orders, we reach farther and farther cells, which makes intuitive sense. Ideally, a Poisson kernel should have an infinite bound reaching every single point in the fluid domain. Okay, let's recap what we have achieved so far. To solve for the pressure P given an input divergence, iterative solvers are often used to get the implicit inversion of Laplacian after k iterations. While the algebraic operations are often done on GPU, these iteration cycles are done on the CPU side, which creates a computational bottleneck because we need to go back and forth between CPU and GPU many times. In contrast, our one-shot convolutional Poisson kernel precisely matches the result of a Jacobi solver of the same order, but it only needs one CPU call per dimension, meaning in 2D we only need 2 CPU calls, and in 3D we only need 3 CPU calls. So to do the pressure projection, we just need to convolve the divergent field with the Poisson kernel to get the pressure, then use it in the correction phase to get the final velocity field. But you might ask, why convolution? To answer this, without getting too much into details, We can think of Poisson kernels as an approximation to the true solution to the Green's function on an infinite domain. Since the equation is linear, we can get the solution for multiple Dirac impulses by summing up the Green's functions. More generally, we can convolve the right-hand f with the Green's function to get the solution. There is a problem though. The full kernel is a dense matrix which is expensive, especially for high number of iterations. What we can do instead is to replace it with separable filters. This turns the O and D complexity into a linear complexity for any rank 1 matrix, but we can easily see our Poisson kernel is not rank 1. This makes us think of a kernel reduction technique to reduce it to rank 1. To do this, we can perform singular value decomposition. While a more familiar decomposition gives three matrices U, sigma, and V transpose, we can instead see it from a different angle, that is, canonical polyadic decomposition, or CPD for short, which is expressing the matrix as a sum of rank 1 matrices. We can then compute the separable filters for each rank 1 matrix to be the outer product of two vectors multiplied by a scalar, which could be the corresponding singular value or the eigenvalue depending on what method we use in computing these vectors. When doing the decomposition of the Poisson kernel, there are a couple of nice things we can do to make using them easier. First, due to the symmetry of the Poisson kernel, the separable filters are also symmetrical for each rank, which is why each pair of filters are shown here with the same color. This means we only need to store one filter for each pair in memory instead of two. Second, we can absorb the singular values directly into the filters by scaling them by the square root of the corresponding singular value. This gives us a more compact representation, which makes the implementation of the convolutional passes easier. To generalize the decomposition from 2D to 3D, we are in trouble though. If we stick to the Tucker view, then we have HOSVD, which stands for higher order SVD. In 2D, we could establish a direct connection between SVD and Tucker view to get the CPD, but in 3D, such connection is not well defined. This is because rank is not well defined for tensors in 3D. To make matter even worse, eigendecomposition in 3D is NP hard. So Tucker view is not very useful in 3D and we need a different method. An alternative to higher order SVD is a special CPD method called symmetric CP, which is compatible to our 2D case in getting the separable filters. Higher order SVD and symmetric CP don't necessarily produce the same results, and each one has its own pros and cons. Higher order SVD is more accurate but not very useful to compute the separable filters, while symmetric CP is useful but not as accurate numerically speaking. It also needs to meet certain requirements such as tensor symmetry for the best results. In our case, we are in luck because Poisson kernel is symmetrical. So we can use symmetric CP to get explicit eigenvectors, which after absorbing the eigenvalues gives us our separable filters in 3D. Although the downside is that symmetric CP is not very accurate, in practice we saw symmetric CP works actually pretty well for the problem. In summary, we are replacing the expensive full kernel convolution with a much cheaper convolution of eigenfilters and then sum them up to get what we want. Doing this is the main reason that our method is very fast, especially because these rank convolutions can be done in parallel on GPU. Computing using these separable filters are the key elements in taming the computational cost of solving the Poisson equation to go from a polynomial behavior down to a sublinear behavior. The ODN complexity means we get order of magnitudes speed up compared to iterative solvers, which only gets better as the fluid domain resolution and the target iteration go up. Before ending this section, let's recap how we put together all the bits and pieces we have seen so far to get a step-by-step algorithm. Given the convolutional version of the Poisson equation, first we grow the Poisson kernel f of order k for a target iteration of k. Then we perform symmetric CP up to a desired rank. We absorb the eigenvalues in the eigenvectors and we get our filters. These filters are symmetrical and identical, so we just need to keep one of them. Now, for example, if we want to solve the Poisson pressure problem, we plug in the pressure and the divergence, and we do a multi-rank convolution to solve for pressure. This involves three convolutional passes, vertical, horizontal, and fiber to get the solution. Okay, let's see how we use the filters. Here you can see everything in action for a 2D slice of a 3D simulation. We expand the input divergence texture in 8 channels using 2 RGBA textures, where each RGBA channel carries the information of a single rank, then do 3 convolutional passes for each dimension, and finally sum them up to get the pressure. The textures you see in this clip represent the results of low-pass to high-pass filters, from lowest to highest frequency, from left to right. As will be explained later, it's important to feed each convolutional pass with the output of the previous pass. It's an easy mistake to use divergence as input for all 3 passes in parallel instead of sequentially. Doing the rank filter convolutions give us a modal solution as the sum of individual local spectral solutions for different frequencies. Just remember, you don't have to use 8 ranks always, just pick up the rank that works best for you. Please note that care must be taken when we deal with choosing the proper rank. While in 2D we get lower to higher frequencies from left to right with a strictly decreasing eigenvalues, the same is not necessarily true in 3D, meaning due to numerical properties of the symmetric CP method, when computing the 3D filters, there is no guarantee that we get sorted eigenvalues. In other words, it's not safe to generate 8 ranks during the composition and then, for example, choose only the first 5, thinking we are capturing the first 5 dominant modes. If, for example, you really need just 5 major modes, do it at the time of the composition, not at the time of application. Another thing is that you can use fewer ranks than what we are seeing here. We found 4 to 6 ranks sufficient in 3D. For 2D, even using the first rank captures more than 85% of the variance, giving us good enough solutions. Was getting the filters all we could do? No. It turns out we can do more. If you look at the filters, you can see a lot of very small values, so we can set a threshold to trim them down without affecting the solution much. This trimming helps with both memory footprint as well as the runtime performance. We can also do a bit of analysis to understand more about the convergence properties of our method when we play around with things like rank and cutoff threshold. For the purpose of convergence analysis, it's safe to consider an infinite domain so we don't have to worry about how much dealing with the boundary condition is affecting our solution. The infinite domain is achieved by dynamic padding, which is just enlarging the domain so much that a certain target iteration never leads to reaching the boundaries of the domain and bouncing back inwards into the domain when collecting pressure values. If we compare the solutions of the Jacobi iterative solver and Poisson full kernel for randomized input without doing any decomposition, we observe the difference between the ground truth Jacobi and our kernel is almost exactly the machine precision, meaning these 2 methods are effectively the same in terms of convergence. We can better see this in the lower right convergence plot, where the residual of these 2 methods match almost perfectly for a target iteration of 6C and a Poisson kernel of order 6C. Since our Poisson kernel is based on a ground truth Jacobi solver, clearly as convergence properties can never beat the ground truth. This means the convergence curve of the Jacobi always acts as a lower bound, where doing anything to the kernel like doing a decomposition, selecting different ranks, or trimming the filters will push the residual up in the convergence plot. We call this upper region the working area. It's up to the user to choose where they want to be in this working area by setting the variables that control the filter's computations. So for example, if we do the kernel decomposition and only use the first rank, we end up having a pretty poor numerical results compared to Jacobi. But as we increase the number of ranks, we see the residual gets better and better. So in this particular example, you see as we use more and more ranks, we get closer and closer to the ground truth Jacobi residual. So for rank like 8, the 2 residuals are virtually indistinguishable. We are only showing the absolute error up to 2 decimals, so the range of the lower left heat map is not really 0, but very close to 0. We can even observe that visually, the solutions to Jacobi and Poisson filters are virtually the same. Now, if we start trimming the filters with a truncation threshold, you see as the threshold gets more aggressive, the residuals of the Poisson filters get worse and worse as expected. Trimming the filters have direct effect on the computational cost. The harder the threshold, the faster the solver, and the worse the quality. Hopefully these examples of comparing different ranks and cutoff thresholds give you enough insight to know how to control the trade-off between the quality of the solution and the computational cost of the filters. To deal with the Neumann boundary condition, we introduced the mirror marching algorithm. Mirror marching is applied simultaneously with convolving the Poisson filters. It's done individually for all 3 dimensions and for each cell in the domain. To understand how it works, consider this example. Assume we have a couple of colliders in the domain, and let's focus on computing the pressure value for a cell marked here as big O. This diagram only shows a 2D slice of a 3D domain, and we're only studying what happens to a horizontal filter, but you get the idea. This is how it goes. To get the pressure value for a random cell O, we need to place the center of the filter on that cell and sample the divergence of the domain in the spots where the filter is overlapping the domain. The convolution involves collecting values to the left and to the right of the filter center. The result of the convolution will be a scalar value, which will be the cell pressure that we want. So say as we are going over the overlapping filter values one by one, we encounter a domain cell that falls into an object, for example, the 9th sample. But we need to sample the divergence for the 9th cell somehow, which of course doesn't exist. The mirror marching algorithm is actually very simple. Start from the central cell O, march incrementally towards the cell that is occupied by a collider, and as soon as we encounter the edge of a collider, bounce in the opposite direction and keep counting. In this example, we want to reach the 9th cell, but on the way we hit a collider at the 6th cell. So we move back 1 cell to go back into the free domain, reverse the marching direction, and count 3 more cells to reach 9, which was the index of the sample we were interested in. We sample the divergence here and use it in the filter computation by multiplying it by the filter value at the cell marked by R. We do this for every single filter value. This way we always have a valid divergence value to use along the Poisson filter. Now let's look at a more challenging case. The sample cell is located far right. Although this cell is not inside any collider, still its divergence value is not valid because marching towards the cell involves going through an object. What we do in this case is keep bouncing off between boundaries until we have counted enough cells to reach the offset value from the center of the filter. This means first we count 6 cells to the right, we encounter a collider, we bounce in the reverse direction without incrementing the counter, take 12 more steps, again reach a collider, bounce back 1 cell, count 2 more cells, and now we have finally counted 20 cells, which matches the original sample index of 20. We sampled the divergence here in the free domain, and voila, we have successfully got a valid divergence value. In general, if the sample is too far from the filter center, we keep bouncing off the colliders. There is no limit on how many times we are allowed to bounce back and forth. The same technique also applies to domain wall boundaries. The important thing to remember is that we always count the free domain cells. So when we bounce at the edge of an object and move 1 cell back, we don't increment our counter. The mirror marching method ensures the neighbor cells at the boundary, one inside the collider and the other outside, have the same values, which satisfies the Neumann boundary condition. The mirroring technique is basically a reflection method, very similar to what's used in spectral methods, but we don't need the pre-computation step unlike the spectral methods. This makes our algorithm very suitable for interactive applications where any collider with an arbitrary geometry can enter the fluid domain, move around, and affect the fluid behavior. We studied the effects of Poisson filtering in the fluid domain while doing the mirror marching and compare it to the ground truth Jacobi. In both cases, we use a spherical collider in a 3D scene and get a 2D slice to do our analysis. As you see, the results are closely matching, especially when we look at the SSIM, which is the structural similarity index. We see very little difference between the two. This means the structural properties of the fluid is not damaged by the Poisson filters. We'll also observe that there is less than 2% error in 99% of the domain, where the object boundaries are almost perfectly satisfied and the wall boundary conditions are 100% satisfied. Let's look at the performance results. We used a decent RTX 2070 GPU in our profiling. Here we compare the baseline Jacobi and our Poisson filters runtimes for the Poisson projection solver as well as the whole simulation. The comparison is based on 3 target iterations for the Jacobi solver and the corresponding filter orders. As an example, for a target iteration of 300 and for 60 by 64 domain, we get around 110 times speed up for the 2D solver and 59 times the speed up for the same solver, but for much larger resolution of 256. For the full simulation pipeline, which involves many other steps in addition to the pressure projection solver, we get 14 and 12 times the speedups respectively. Similar speedups are also achieved for the 3D case. The runtime gains in 3D are relatively less than 2D, but still we observe an order of magnitude speedup in 3D as well. You would also notice that we gain more speedups from the Poisson filters as we increase the target iteration both in 2D and 3D. This is an expected behavior because Poisson filters turn a polynomial computational cost into a sublinear one. So our method shines even more when higher quality simulations are of interest. This sublinear behavior is even more evident in this plot. Compared to some of the well-known iterative solvers like Jacobi, Red-Black Gauss-Seidel or RBGS for short, and preconditioned conjugate gradient or PCG for short, the cost of our method barely increases with higher target iterations. Also, for a given desired residual, our method performs an order of magnitude faster compared to the others. Although the residuals we get from Poisson filters are not a match to something like PCG, we find the results quite satisfactory for real-time applications. The convergence cost plot might be a bit tricky to be understood properly, so let me try to explain it. We have 3 dimensions in this plot: convergence and cost as the 2 axes and a color-coded target iteration, which goes from the first iteration, shown here as blue, to the last iteration, shown here as red, to indicate the increase of the target iteration for each solver. Let me give you an example of how we can read this plot. Say we want to compare and order 200 Poisson filters to RBGS. We see for the same desired residual, Poisson filters run approximately 4 times faster than RBGS, and for the same desired cost, the Poisson filter solution results in a residual that is almost twice as better as RBGS. Okay, time for some demos. We can run simulations at interactive rates for quite high resolution domains where boundary conditions are pretty well satisfied even for challenging scenarios like the purple bunny. For the pressure projection alone, we achieve up to 30 times faster solver runtimes in 3D and up to 100 times faster runtime in 2D. For the whole simulation pipeline, the speed up factors are about 10 times in 3D and 15 times in 2D. Here you can see an example of forward Poisson solve for density diffusion. You can particularly probe for the behavior of the smoke around the bunny collider surface. Also notice adding the Poisson filter-based diffusion to a domain with about 9.4 million voxels only adds about 10 milliseconds to the whole simulation pipeline, which is an order of magnitude faster than iterative solvers. We also experimented with solving the heat equation on quad mesh surfaces. We didn't consider the curvature of the space, so our results are not necessarily accurate, but this demo shows a potential application of Poisson filters for future work. On the left, you see the heat diffusion, and on the right, you see a few examples of how vertical and horizontal filters are applied to the curved surface. Our fast pipeline also allows for live editing this disastrous situation at the gas station. There are 2 huge volumes in this scene. The volume containing the car has around 11 million voxels, and the tanker in the back has around 5 million voxels. We can move the domain around to experiment with the scene until we are satisfied with the effect. Running the simulation at interactive rates is very useful for VFX artists to quickly iterate on their ideas. Another hypothetical example is this scene where you see a swinging tire on fire hanging from a branch. Any object in the scene can be a collider or smoke or heat emitter. The artist can switch the role of the tree from being a collider to an emitter, then play around with the simulation parameters such as smoke dissipation to get an immediate visual feedback. The scene is also a tough example to stress test our Neumann boundary treatment through the mirror marching algorithm because the smoke has to make its way through the tree leaves without too much dissipation. We have also made a fun demo where you can use a gamepad to set anything visible on fire. The flamethrower has a mechanism to spray and deposit a pre-mixed fuel on any surface in its reachable surrounding and then set them on fire. The fire burns according to an adjustable fuel burning rate until it runs out of fuel. The cool thing is we can set any object in the scene on fire without any pre-decided scripting. This prototype is as close as we could get to a genuine gameplay. Now in this demo, we use a gamepad to control a character through a smoke field where the character's skin mesh collides and perturbs the smoke. Because the human collider geometry is constantly changing, we're not using simplified geometry like a cylinder as the collider here. Instead, we actually process the skin mesh of the character at each frame to get the accurate collider geometry, then use it in the boundary treatment step. And here is another fun demo where we use the same technique to extract an accurate emission mask of the character's skin geometry and use it to emit fire and smoke. I'll let you enjoy watching the Burning Man for a while. Let me wrap up this video by quickly going over some points about the implementation of the Poisson filters in your code. We have released the code. In there, you would find the Python code to generate the filters based on your own custom simulation settings. We have also included a large database of 2D and 3D filters that are ready to be plugged into your C++ or HLSL shader code for many different target iterations. Computing the Poisson filters, especially for 3D applications and very high quality target iterations, might take some time, so you might find this pre-computed filter database useful. Having filters either from the generator or the database, you can directly copy them into your code. Choose any of the available orders that suits your application. Then, for example, in a HLSL code, you would have a bunch of float fours where rank values are stored in RGBA channels. For example, for 8 ranks, it's sufficient to use 2 arrays of float 4, each storing 4 ranks. The filter values are not truncated by default, so based on your runtime needs, you can further truncate them to get rid of very small values to save some memory and get faster runtimes. After trimming the filters, and because of the symmetry of the filters, you can just store half of each filter and reconstruct the rest when you use them in your convolution loops. This means the memory footprint is not only small, but it also remains small for very high filter orders. This plot shows values for different filter cutoff thresholds shown by sigma. You can compare the untruncated memory footprint shown by blue with a few examples of some other cutoff thresholds. The memory footprint after truncation demonstrates a sublinear behavior, meaning it barely increases as the filter order grows. Remember, a sublinear behavior also means it's safe to apply mild to aggressive truncations without really hurting the solution. Since the CPU-GPU implementation is not provided in the code release, I'm going to highlight some important details that you need to know for implementing the solver properly. Let's look at an example of using 8 ranks for computing the Poisson pressure, where the input-output are 2 scalar fields, divergence and pressure, stored in single-channel flow textures. First thing we need to do is to expand the single channel divergence into 8 channels for 8 ranks. This means we need to copy its values into 8 channels in 2 RGBA textures. We also would like to minimize the read-write latency on this GPU side, so we need to use a ping-pong method where we swap the ping and pong on the CPU side at each turn. A full convolutional pass of the Poisson filters involves convolving in 3 directions for a 3D domain: fiber or depth, horizontal and vertical. It's important to feed each pass with the output of the previous pass. A common mistake we have seen in adopting our method is to use the divergence as the input, for all passes. So you want to be careful about this part. You would also need two shader codes, one for convolution and one for summing up the results of each frequency modes in a channel at the end to get the full solution for the pressure. Another common mistake is to sum up the channels after each convolution pass. Keep channels separate until the very end where you want to sum the rank solutions. Okay, with all this, let's do the convolutions. Starting from the expanded divergence in two float 4 textures, we do the fiber convolution and save the results in two float 4 temporary textures. Remember, R14 and R58 means the first and the second 4 ranks that together give us 8 ranks. Now back to CPU, do a pinpoint swap, do a horizontal convolution, and save the temporary results to be used for the next convolution round. Repeat the same steps for the vertical convolution. At the end, we're ready to collapse all 8 channels into one to get the final scalar values for the output pressure. We pass the output of the vertical convolution, which already contains the results of all 3 convolutions, to a simple shader that does the summation for us. And voila, we get the final pressure. Doing a filter convolution in the shader code must be pretty straightforward for most people familiar with GPU programming. That being said, it's a good idea to go over some details because seemingly small details can have a huge impact on the optimum performance that you want to get out of your solver. To be consistent with our hypothetical example of using 8 ranks, first we need a bunch of float 4 variables to hold the results for convolutions, as well as the filters and the domain samples. We keep them divided into 2 groups, R14 and R58. We define macros to use the same shader for both rank groups. This helps with the speed up because we keep the filter values accessible directly in the same shader instead of sending the data through buffers. Next is setting the variables for the convolution loop. For a hypothetical case of Poisson filter order of 60, the full filter size is 119. It's also convenient to define a half cut, which controls how we want to trim the filters in the truncation step. It's called half cut because we only need to worry about the indices on one half of the symmetrical filters. Alternatively, you can copy already truncated filters into your code, but generally speaking, it's a good idea to have the full filters in your code and use half cut to experiment with the truncation value to observe their effect on the fluid's behavior. Remember to hard code these values and use const for efficiency. Now for the convolution loop. Starting from top, we want to compute the pressure for the current cell. So we need to make sure the middle of the filter is exactly aligned with the current cell. So we set up the loop such that the offset starts from the leftmost index of the filter after truncation all the way to its rightmost index. Filter values are the same in all directions, so we just need to construct an int3 for the offset ID that only traverses the current direction of interest. We then use this offset ID to sample the input domain as well as the filter value corresponding to those sampled cells to do the convolution step. The sum variable keeps track of the accumulated values so far in the convolution loop. Please remember this is a typical filter convolution sum that works with float 4 textures and shouldn't be confused with the final channel rank sum, which must happen in a separate shader. It's also important to use unroll for the loop when compiling the shader to get the best performance. And that's it, you should be good to go. What we haven't covered here is the implementation of mirror marching. You can see our paper for the pseudocode, and you can find a Python implementation of the boundary treatment in the release code. You can check out our repo for multiple demos, Python implementation of the boundary treatment and filter convolution, and functions that help you with performance versus quality analysis. The repo also comes with a detailed documentation that presents mathematical context of different functions if needed. There are also practical tips on how to use the filters properly for the best results. So what's next? We would like to apply our method to viscous fluids and consider addressing the Dirichlet boundary. Current way of computing filters is intrinsically slow for very high filter orders due to the nature of the problem being MP hard. It would be interesting to find faster decomposition methods. We also like to generalize our method to the curved surfaces. Since the application of the Poisson equation is not limited to Eulerian fluid simulation, it would be nice to explore the usage of our filters in other domains such as image inpainting and surface reconstruction. Finally, using our accelerated solver in multi-grid methods as a smoother to make them even faster through reducing their cycles seems to be a very promising next step. Thank you.